Q&A time. Any question? You can just turn on the mic and speak up, or you can post your question on Slack. Well, since no question, can I ask a standard question, if you won't mind?
Of course.
Thanks. Thanks for your presentation. I see in your analysis, I certainly understand, the system is very complex. You need to have the mathematical convenience and assumptions in order to carry out the analysis. In the practical point of view, how do you see, some of the parameters obviously assumed to be exponential or Poisson and things like that? I can see, the generation of some of the parameters as Poisson is often very reasonable. But how about some of those coherence time and some other things that are assumed to be exponential? I wonder whether you are aware of some kind of validation of some of those distribution?
That's an excellent question. So when people analyze these kinds of systems, they usually assume some sort of noise model. For example, some noise model on the quantum memory architecture of the switch. And in certain noise models, you do have this kind of exponential degradation in fidelity. So I think one may argue that at least that assumption is sort of justified. The Poisson entanglement generation is sort of justified if you look at the system operating in discrete time. Then it's more of a geometric, it gives rise to a geometric distribution. So then we have Poisson in the continuous time model. What our model and what our analysis doesn't really account for here is the final fidelity or the average or any kind of description of the fidelity that results from these end-to-end entanglements that are being created. So that's something that could definitely be improved on, but I think it would be a kind of a tough thing to tackle.
Thank you.
Mm-hmm.
Any other question?
I have a question.
Yeah, go ahead, please.
So I was wondering, can you say that your switching policy is in some sense like optimal or tight? Like, given the capabilities of the system, this generates as many pairs or pairs as much of the time as is possible? Or are there places where you know it's not? Thanks.
Great question. So in the case where we considered only one quantum memory available to each link, that's the buffer size 1 system, we actually did do a complete analysis and we looked at all possible randomized switching policies that could be represented by that Markov chain. And we saw that that blue triangular sort of envelope that you saw in some of the plots was actually very tight. So meaning that there exist policies on that envelope, and you cannot do better than that. Now, for the buffer size 2 system, we didn't do a complete analysis because it gets a little tedious. So we actually only looked at a subset of the possible randomized switching policies. So we just know that there's kind of an achievability result that you can do better than time division multiplexing, but we don't know whether you can do better than the plots that you saw, the envelopes there.
Okay, thanks.
Mm-hmm. Thanks for the question.
Any other question?
The other question is, is there any hope of a limiting result as the buffer size maybe grew? Like if the buffer size was very large, is the behavior in that area sort of clear or not?
So within the context of this problem, for me, it's very hard to sort of guess what would be the result of that. Now, if I look at a system that only generates n-partite entanglement, where n is constant, right? So only bipartite, like we saw in the previous talk, or tripartite, and so on, then we can easily kind of look at the limiting behavior as the buffer size goes to infinity. But in this scenario where n can be varied and you can generate different types of entangled states, it's hard for me to even generalize this to like a larger, or to a switch that has, let's say, 3 quantum memories per link and so on. So, but I think it's actually an excellent thing to study and to kind of look at what happens when you continue to increase buffer size, because that could be a very interesting sort of design guideline for these types of devices in the future.
Okay, thanks.
Thanks.
Any last question? Well, if not, we